person linear approximation.
Here's the target right here. Oh, nice.
Hi everyone. So the plan for today is to finish the material for the course, which includes estimating their linear approximation and also cover a derivative of inverse trigonometric functions. And I remind you that next time I'm going to do some reviews, so if you have any suggestions, any questions to discuss next time, send me an email. Okay, so I want to discuss the following problem. Suppose you are given a function and you want to write down its linear approximation at some point. Well, we know how to do this, no problem. We find the equation of the tangent line and use it. The question is, well, how large would the error be? We know how to know whether we get an overestimate or an underestimate. That involves the sign of second derivative. The question then is, how large is the deviation between the approximation and the actual value? Up to now, we didn't have any tool to know this. And well, now I will discuss how to find such an estimate, how to know a priori, before you actually make a calculation of the actual value, what will be there. Well, not exactly, but an estimate of this. And I will start from something which will look unrelated. I will try to justify the mathematical point that I'm going to make using physical intuition. So before this, I'll discuss just a tiny bit of physics.
Super.
So first thing that we will discuss is, suppose you have an object and the velocity, the speed of this object is not changing. You keep it fixed at some number v. What is the position of this object at time t? Well, that's the answer. The position at time t used to be at time t naught plus whatever distance the object has moved. The velocity times the time it has passed. So very simple equation. Once again, position at time t is the position at time t naught plus the velocity times the time that has passed since t naught. And v is the velocity. Well, that's what happens when the speed is constant. When the speed is not constant, but say nearly constant, so almost not changing, what happens? Well, of course you can replace this by an approximate quantity. So if velocity is only approximately equal to v, then you have this equality, but only approximate. If my car moves not exactly with 60 kilometers per hour speed, 60 kilometers per hour, but kind of 60 kilometers per hour plus minus 1, well, still I can know approximately what will be the position in 1 hour. It will pass approximately 60 kilometers, well, plus minus 1 kilometer. And that's essentially the linear approximation that we use. Recall that v is just the derivative of the position. Velocity is the derivative of position. So that's basically the linear approximation to the position function using the position function at time t naught plus the velocity at time t naught, assuming that the velocity is not changing much. Well, next question is how to know what is the difference? How large is the error here? Suppose that I know that my velocity is changing, but not much. Well, let's put some so I want some quantitative measure on, well, how fast my velocity is changing. Suppose that I know that my velocity is changing, but changing not too fast. What does it mean? That the rate of change of the velocity is not large. It means that the acceleration is bound. So suppose that I know that the acceleration is not bigger than something. What will I be able to say about this approximation? How good it is? Well, let's see. So I'll discuss first what happens if acceleration is constant. Well, that's the answer. The position in time t is what it used to be at t naught plus the velocity at t naught times t minus t naught plus a times t minus t naught squared divided by 2. So it's really easy to check that this indeed is the description of position of an object which at time t naught is at this place, y of t naught, whose velocity at time t naught is y prime of t naught, and whose acceleration is a all the time. So y double prime of t is just a, and that's the acceleration. So now I just talked about kind of high school material. What happens if the acceleration is constant? Well, the position is described by such and such formula. Now I want, well, one extra step. Suppose all you know is that the acceleration is, well, it's not constant, but it's no more than a. Suppose we know y of t naught, y prime of t naught, and that the second derivative, the acceleration, is no bigger than a. So now I have a car, well, an object, which is at time t naught, it is right here, y of t naught, whose velocity is also given to me, it's y prime of t naught. And now I know that it cannot accelerate faster than some particular number a. Well, that's kind of what happens to a typical car. We cannot really make it accelerate too fast. If we press full gas, well, it will only accelerate up to its kind of physical capacity of acceleration. It can't burn too much fuel, can't accelerate too fast. So suppose that we know only this, that the acceleration is bounded by some number a. Well, question. How should we, well, what should the driver of this car do to get as far as possible? So we impose the condition that our driver at time t naught is at position y of t naught. Its velocity, the velocity of the car, is y prime of t naught, so those we can't change. What the driver can change is its acceleration. It can press more gas or less gas. But we know that for some reason, say because it drives a slow car or not very powerful car, its acceleration is always bounded by some number a. So what should it do to get as far away as possible from us? Well, of course, press full gas. Accelerate as fast as it can. That's kind of obvious. Well, let's write it in formula. At time t, it will get only as far as it would have gotten if it pressed full gas and used the full acceleration here. So it will be y of t naught plus y prime of t naught times t minus t naught plus a t minus t naught squared divided by 2. So once again, if the driver presses full gas, well, he will get a time t on this position. If he chooses any other strategy, well, press gas, release, well, anything, then it will not get as far. So his actual position will be smaller than this thing. Okay, but now we have a bound on the actual linear approximation. Look at this. Just rearrange y of t, the actual value of the function, minus y of t naught plus y prime of t naught, t minus t naught, is at most a t minus t naught squared divided by q. Let's read this not in formulas but in words. The actual position differs from the position that we would get from linear approximation or from approximation with constant velocity at most by that much. So now we have a formula. Well, this formula is about cars. We thought about y as the position of a car, but actually it works for any function. We didn't really have to use it as car. We only use it as a car here in our physical intuition. But any function can describe, well, any continuous function can reasonably describe motion of a car. So we have this for any kind of function. So let me rewrite this. And now using our usual notations. If f of x is a function and f double prime of x is smaller or equal than some number, I'll call it m this time, then f of x minus f of x naught plus f prime of x naught times x minus x naught is at most m times x minus x naught squared divided by 2. So the error in the linear approximation is bounded by such a quantity. Actually, I was just a little bit sloppy here. I said that the acceleration was at most a, but my driver could kind of cheat. He would well say, well, yes, my acceleration is at most a, but now I'll accelerate in the opposite direction. And now I don't have any bound. I can accelerate as fast as I want because I didn't say that y double prime is bigger or equal than minus a. Well, so to prevent this, I'll have to impose another condition, that the absolute value of y double prime is smaller than a. Then I will be able to say that, yes, we actually didn't get that far away from us. So a more precise statement is as follows. So this statement is only a kind of tentative, but the actual statement is as follows. So here, initial important statement. So let's substitute this for important. If f of x is a function and f double prime at point C, so the absolute value of this thing is smaller or equal than m for C between x naught and x, then absolute value of f of x minus f of x naught is x minus x naught smaller or equal than m times x minus x naught squared is larger than 2. So let me discuss the small changes that I made in this statement versus this one. So I introduced some absolute values. So now I disallow it to accelerate too fast in the opposite direction. Here I put an absolute value to say that, well, the error is not, well, it's bounded in magnitude. I mean, I disallow the error to be too large positive, and also I disallow it to be too large in negative. And I forgot closing bracket here. And another small change that I made is I put this bound on the derivative only for values between x0 and x. But that's okay. I only need to control my driver from the time t0 to the time t when I measure its position. I don't care what happens afterwards, I don't care what happened before. So that's the statement. Let me reformulate it in kind of words, i.e. absolute value of error in linear approximation of f x using the value of x naught.
I didn't know.
So the absolute value of this error is at most m times x minus x naught squared divided by 2, where, so I want to take m larger than all the values of the absolute values of second derivative. So let me just take m to be the largest of those. So let me take m to be the maximal value of absolute value of second derivative for c between x0 and x. So that's an equivalent statement. Just the same thing that I stated here, I restated here, but using words. So every time I make a linear approximation, I can know a priori, before I do any calculation, well, almost any calculation, how large my error will be. It will be no larger than this thing, where m is the largest value of the second derivative. So it might be a little bit abstract, but let's see in some examples that it's actually, well, pretty easy. So example. Use linear approximation to cubic root of x at 1000 to compute cubic root of 1000. Estimate the error. So let me explain this question. You might remember that, well, 2 or 4 lectures ago, we actually used linear approximation to try to estimate what is cubic root of 1001. Well, it was about 10, a little bit larger. We had this linear approximation. But now the question is not about the actual value. Now the question is, suppose you get the answer from linear approximation. And suppose you also get your answer from calculator. How large will be the difference? Well, right here. The difference will be bounded in absolute value by such an expression, where m is the largest value of the second derivative. So we should start by finding the second derivative. Solution. My function is cubic root of x. Its derivative is 1/3 x minus 2/3. The second derivative is minus 2/9 times x to minus 2/3, minus 5/3. The absolute value of the second derivative. Well, I have here minus and then something positive. My x is positive, so this whole thing is positive. So 2/9 x to minus 5/3. Next part, I want to find how large my second derivative can get. So I know this expression. Now I want to find what is m. M is the maximum of the second derivative, absolute value of second derivative of x between what and what. So I'm only interested, so I'm doing my approximation to this function, to the value of the function at 1001, using its value at 1000. So I'm only interested in x between 1000 and 1001. So here I'm taking maximum of x between 1001 and 1000. So I'm interested in maximum of 2/9 x to minus 5/3 when x is between 1001 and 1000. So up to now I just used basically the formula. This formula, I found the second derivative, I plugged it in. Next question, what is this number? What is the largest value that this function 2/9 times x to minus 5/3 can assume on this interval from 1000 to 1001? So once again, the question is, we have this function 2/9 times x to minus 5/3. We look at this function only in the interval from 1000 to 1001. What is the largest value of this function? Yes. So it attains the maximum at the point 1000. Why? If you look at this function, what is increasing or decreasing? Well, look at it. It's 1 divided by x to the power 5/3. If x increases, x to the power 5/3 also increases. So 1 over it decreases. So this function is decreasing. Decreasing function. Well, but now imagine a decreasing function on some interval. You have an interval, over it you have some decreasing function. Well, of course it is the largest at the left-hand point. So this function is the largest when x is 1000. So it's 2/9 times 1000 to minus 5/3. Or in other words, it's 2/9 and 5 zeros. So once again, the argument for this step was this function. If you increase x, the function becomes only smaller, so the maximum is, well, at this left-hand point. Okay, and next we'll use this statement. Absolute value of the error is at most, so m, which you found to be 2/9 100,000 times x minus x naught, which means 1001 minus 1000 squared, and divided by 2. Or if you simplify, it's just 1 over 900,000. So look what happened. We did not compute either cubic root of 1001, nor did we compute the linear approximation. But we do know how large the difference between those will be. Well, it's not that we know exactly how large it will be, but we know that it will be no larger than this. So a priori, before we actually compute anything, we know that the approximation will be, well, pretty good. Approximately 6 correct digits. Okay, so now maybe any questions? Yeah.
What is the function of the critical
Okay, so the question was, what if this step wasn't as easy? What if my function is not decreasing, not increasing? What if it increasing, then increases, then increases? Well, then we'll have to do the usual trick of finding the value at the critical, well, finding the critical points, finding the value of the function at the critical points, comparing those values to the values at the endpoints, and finding the largest one. But usually, well, I mean, usually when we do approximations, we use simple functions, simple in the sense, not very complicated, not in a technical sense. And then the second derivative is not very complicated, and then it's kind of either increasing or decreasing. But if it isn't, well, you have to do the computer procedures. Other questions? Okay, so let's do another example, also simple one. Example, find the linear approximation side of 2 degrees and estimate there. Okay, so just to find the linear approximation, well, it's not very complicated, we know how. We know that 2 degrees is not that 2 degrees is pretty close to 0, so we'll use the linear approximation in 0 as the most sensible thing. Then we know that to actually find the linear approximation, we'll have to convert degrees to radians. So solution, use f of x sine of x, x naught equal to 0, sine f prime of x, first we need f of x naught is sine of 0, which is 0, f prime of x is cosine of x, f prime of x naught is cosine of 0, which is 1. The linear approximation is sine of x is approximately 0 plus the derivative times x minus 0, so it's x. sine of 2 degrees is, well, we first convert these to radians. Sine of 2 times 1 degree is pi over 180. So it's sine of pi over 90. And this is approximately pi over 90 using this linear approximation. So finding the linear approximation, well, nothing new. I just recall how to do this for the function sine. To estimate the error, well, let's find the second derivative. And double prime of x, derivative of cosine is minus sine. The absolute value of second derivative is, well, let's think for a second. I'm interested in interval where x is between 0 and pi by 90. So sine of x is positive here, so that's exactly the absolute value of that double prime. I now can ignore this minus sign. And m, which is the largest value of the second derivative, absolute value of second derivative for x what interval should I use? Pi over 90 and 0. Yes, so I'm using the approximation at point 0 to evaluate sine of pi over 90. So this is maximum of sine of x for x between 0 and pi over 90. Well, let's think about this function sine when x is between 0 and pi over 90. Can we say that it's increasing, decreasing, or? Yes, it's increasing. So if you imagine graph of sine, yes, in general, x sine of x. In general, sine of x is neither increasing all the time nor decreasing all the time. But that's not where we're interested here. We are only interested in the interval from 0 to pi over 90, which you know is a pretty small number. So on this interval, function is increasing. So this is, well, the largest value is attained at the right endpoint. So it is sine of pi over 90. Okay, and now we have the following estimate. Absolute value of the error, which is sine of pi over 90 minus pi over 90. That's the error. So the actual value minus the linear estimate is at most sine of pi over 90 times pi over 90 minus 0 squared divided by 2. So we get that this is sine of pi over 90 times pi over 90 squared. So, well, so basically it is quite similar to the previous exercise with one small difference. Now my function, second derivative, is not decreasing but rather increasing, and I had to evaluate it at the right hand. And I got some estimate that the error is at most this much. Well, it is itself a pretty complicated expression, but, well, approximately I can tell you what it is. I mean, pi over 90 is about 1 over 30. Sine of pi over 90, well, we know it's about pi over 90, which is 1 over 30. So this is about 1 over 30 cubed. which means 1 over 27 thousandths, and divided by 2, so well, kind of 1 over 50 thousandths. So we know that this error will be, once again, pretty small, smaller than about 1 over 50 thousandths. We don't know exactly what the error will be, but it will be no larger than this thing. And maybe another small remark. In this particular example, well, we don't have a way to know the sign of this error. We don't know whether this pi over 90 is an overshoot or an undershoot, overestimate or an underestimate. Why? If you look at the second derivative at the point 0, the thing that we talked about is over and underestimates. Well, it's just sine of 0, which is 0. Doesn't tell you anything. But still, whatever it is, positive or negative, this error will be at most this number. Okay, so maybe any questions? Okay, so let me just make a small remark. If I wrote this on the exam, I will probably get something like -1 point because I didn't explain this step. I mean, I drew the picture, but I should have written also that this function is increasing. So if your solution is not readable without additional explanations, well, it's a bad solution. So you should make it readable even without extra explanations. Okay, so now let's switch to another topic. So basically here on this topic we expect you just to know to solve these simplest kind of problems. Estimate the error in linear approximation for a given function. You should know that it's just inequality, that is not the actual error. And of course we cannot compute the actual error if we cannot compute sine of pi over 90. We can estimate it. So you should know that this is inequality. You should know that this constant is the maximum of the second derivative and be able to evaluate such a maximum. Okay, so now let's talk about inverse trigonometric functions. So first function we are going to talk is arc sine. Y is arc sine of x. Sometimes we also write as follows. Y is inverse sine. So in the same way we write kind of y is f to the negative 1 of x, meaning it's the inverse function. We also sometimes write y is inverse sine of x. And the meaning here is as follows. This happens exactly when sine of x and sine of y is equal to x. So we say that y is the arc sine of x when its sine is x. Or in other words, arc sine of x is the number whose sine is equal to x. Well, there is a problem with this definition. There isn't just one number whose sine is equal to a given x. If I tell you what number has sine, say, equal to 0, well, I'll come up with a bunch of those. Sine of 0 is equal to 0, but sine of 2 pi is also equal to 0, sine of 4 pi is 0. So here we make a restriction. It's the number between negative pi by 2, and pi by 2. And now there is only one value of y, for which sine of y is equal to x. Well, and also, there is another small problem. If I tell you that x is, say, well, you will be in trouble. Why? If you want to find some y such that sine of y is equal to 2, well, there is none. Sine is always between -1 and 1. So here we have a restriction on the domain of x. The domain is for x between -1 and 1. Let's try to sketch the graph of this function, inverse sine, arc sine. Well, we know how to find the graph of an inverse function. We should just take the graph of function and reflect it with respect to y equal to x. X is the line. So let me first draw the graph of sine. Sine of y looks like this. And I only restrict to the interval from pi by 2 to negative pi by 2. And this is 1, and this is negative 1. And now I will flip the axis. I'll get the graph of arc sine. So it will start at -1, end at 1. -1 it will be minus pi by 2. We will have now not horizontal tangent but rather vertical. And end up at pi by 2. So that's the graph. It only exists when x is between -1 and 1, and at these points, well, it just ends abruptly. It is sine, well, it is sine. Well, I just labeled my axis here to be y, and this is sine of y, and you can say that it's x sine of x. I wanted this to be consistent, yes. I mean, after I reflect this graph, this becomes the y-axis, the arc sine axis, and this axis sine of y becomes x-axis. So I wanted this y to be the arc sine and this sine of y to be x. Well, but basically, regardless of the labels, that's the graph of sine. And that's the graph of arc sine. Okay, so we have these graphs. Next, let's discuss several simple values for arc sine. Arc sine, say, 0. So by definition, arc sine of 0 is the number between minus pi by 2 and pi by 2 whose sine is equal to 0. What is this number? 0, yes. Arc sine of 1. It's a number between minus pi by 2 and pi by 2 whose sine is equal to 1. What's this number? Pi over 2, pi by 2, yes. Similarly, arc sine minus 1 is,
What is arc exactly?
sorry? What the arc stands for?
Is arc just inverse?
Well, yes, in this case, yes. So for historical reasons, so first let me answer this question, then I'll talk about the name. So arc sine of -1 is a number whose sine is -1, so it's minus pi by 2. So we'll add several more lines to this, but let me address this question for what is arc and arc sine, because it has an answer, quite simple answer. So I will now explain what is the arc in this arc sine, and recall how we define sine. If we have a circle of radius 1, and we have an angle of x, then, well, this is the sine of x. Okay. Now, what is x in this case? It's the angle measured in radians. But radians in this case is just the length of this arc. So this has length x. And the arc sine is, so sine is the operation of taking this arc and finding this length. Arc sine is the operation of taking this length and finding this arc. And that's where the arc comes from. It's finding the arc. But, well, the more modern notation is just the inverse function. So on your calculators, you'll see, well, the bottom is sine raised to power minus 1, and you should not confuse it with just 1 over sine. So, because it's easy to confuse with 1 over sine, well, sometimes you prefer to write arc sine, and I personally prefer to use it always. Both notations are okay. Okay, so back to this. What is arc sine? We'll say 1/2. Some opinions. So it is the number whose sine is equal to 1/2, and it is pi over 6, yes. So sine of 30 degrees is 1/2, and 30 degrees is pi over 6. And, well, in just one more value, arc sine of square root of 2 by 2 is pi by 4, because sine of pi by 4 is square root of 2 by 2. All this is, well, kind of high school material, no, well, nothing from calculus. Now let's talk about the derivative of sine, of arc sine. Well, first of all, we didn't see what is the derivative of arc sine up to now. We never discussed this function. But we already developed all the methods to actually find this derivative. What do I mean? Well, we have a different definition. Here, arc sine is the function y, which is defined implicitly by this equation. So y is arc sine of x satisfies sine of y is equal to x. So the title here is derivative. Okay, so it is the function which is defined implicitly by this equation. How do we find its derivative? Oh, of course, by implicit differentiation. So differentiate implicitly. Derivative of left side is cosine of y times y prime. Derivative of right side is 1. So y prime is 1 over cosine of y. Okay, it is an answer, but it's not really a satisfactory answer. What do I mean? Well, it's not a really good idea to say that derivative of arc sine of x is 1 over cosine of y, where y is a cosine of x. It's kind of strange. We want the derivative of function of x to be a function of x, not of y. So let's convert this expression into a function of x. The first operation I'll do will be a little bit strange. I'll write it as square root of cosine squared. Well, yes, it is a strange operation, but legitimate. Square root of something squared, if this something is positive, is exactly this something. And cosine of y here, it is positive because, well, y is between negative pi by 2 and pi by 2, so cosine is positive. So I didn't introduce any troubles in this step. No, why did I do this? Because I remember there is an identity with cosine squared and sine squared. Sine squared plus cosine squared is equal to 1. So I can take this and write it in this way. Square root of 1 minus sine squared of y. So here I use that sine squared plus cosine squared is equal to 1. Well, but now I can quite easily convert this to an expression about x. How? Well, I know what the sine of y is, just x. So this derivative of arc sine of x is 1 over square root 1 minus x. And this formula is important to remember. I mean, this derivation is, well, you should understand it, but, well, not exactly remember it. Just understand it. We can find the derivative by just implicit differentiation. But this formula should be, well, automatic. You should know it as well as the fact that derivative e to x is e to x, something like this. So, remember this formula. And later in the next course, when I'll find it will be useful for integration of some functions. So you will see it once again. At least once again. Okay, so maybe any questions about arc sine? Well, so now we'll repeat a similar procedure with other trigonometric functions. We'll talk about inverse of cosine, inverse of tangent, and for each one of those we'll draw the graph, we'll find some values, and find the derivative. Or at least state the derivative. So arc cosine. Y is arc cosine of x if, so if and only if cosine of y is equal to x. So once again, we have a similar definition. Y is the inverse cosine of x if and only if cosine of y is x, which means arc cosine of x is the number y whose cosine is equal to x. Once again, we have the same problem. There is not only one number y like this. We have to restrict to some range. And in this case, the range is for y to be from 0 to pi. As y moves from 0 to pi, cosine moves from 1 to minus 1. Let me on this board draw the graph of cosine. X, y, cosine of y. So on this interval from 0 to pi, the cosine goes over all possible values for the cosine. And also, same problem. Not every number is cosine of some. Only numbers between -1 and 1. So once again, we have the domain of this function is for x between -1 and 1. Okay, then let's look at this graph and try to reflect it. To find the graph of our cosine. So cosine of y now becomes x. Arc cosine x. We will once again have on the x-axis two important points, -1 and 1. At -1, the function will be equal to pi. It will have now not a horizontal tangent, but rather vertical after the reflection. And at 1, it will become zero. And once again, we'll have vertical tangent, and the graph looks like this. And these values are pi, pi by 2, 12, 0, 2. Let's discuss some important values for our cosine. Our cosine of 0, 1, -1. So what is our cosine of 0? Once again, the definition is the number between 0 and pi whose cosine is equal to 0. What is it? Pi over 2, right. Our cosine of 1, 0. So cosine of 0 is equal to 1. Our cosine of -1, pi, yes. So once again, even though, say, our the cosine of minus pi is also 0, or is also -1, we choose pi, well, because of this convention. And this is nothing but convention. We could have chosen a different interval, it would work as well, but this is the convention. Okay, next, let's discuss our cosine of 1/2. So now it's the angle whose cosine is 1/2, so it is pi by 3. Arc cosine of -1/2. Okay, that might be a little bit trickier. 2 pi by 3, yes. So I can draw a picture for this. So you should imagine the unit circle, cosine being -1/2, and the angle should be this angle. So if this is -1/2, and this angle is 60 degrees, and this is 120. So this is pi by 3, this is 1/2. Okay, and did I miss anything? Well, arc cosine of square root of 2 by 2 is pi by 4. Well, I will not derive the derivative of our cosine in the same way I did for arc sine, because there is, well, a fantastically simple formula that relates arc sine and arc cosine. It looks like this. Arc cosine of x is pi by 2 minus arc sine of x. So in fact, this formula, this function arc cosine, is not really a new function. It's more or less the same as arc sine, but taken with minus sign, minus sign, and shifted by pi by 2. Well, the reason is, well, that's a reflection of such a formula. Cosine of y is sine of pi by 2 minus 1. So, if you know that some number has cosine, if x is cosine of some number, you also know that it's sine of pi by 2 minus this number. Okay, this leads to such a formula, arc cosine of x, derivative is minus 1 over the root of 1 minus x. So in a way, this function is, well, simpler than, well, not simpler, but exactly as complicated as arc sine, because it's basically just arc sine, but pi by 2 minus arc sine. Okay, so questions about arc cosine. Okay, there is one more important function to discuss, and that's arc tangent. Well, you can guess what it is. Y is the arc tangent of some number x, when tangent of y is equal to x. Just let me recall that tangent of something is sine of this something divided by cosine of this something. Tangent of y, sine of y divided by cosine. Well, as usual, we should, there is not only one y for which the tangent is equal to a given x, we should restrict to some interval, and here the convention is y is between minus pi by 2 and pi by 2. And that's, well, a very reasonable convention. If you look at the graph of tangent, when you have never seen it, let me draw it for the first time. So at 0, tangent is 0. Then it increases. And then when x approaches pi by 2, the denominator here, cosine of pi by 2, is 0. So denominator approaches 0, and the tangent becomes infinitely large. So this function is a vertical asymptote, and also a vertical asymptote here. So that's the graph of our tangent. Well, in fact, the full graph of tangent continues. This periodic function repeats itself. Now, any number, both positive and negative, bigger than 1 or smaller than 1, can be a tangent of something. You see that this tangent goes all the way from minus infinity to plus infinity. So the domain here is all numbers. And the graph of arctangent looks like this. X and arctangent of x. Well, what used to be a vertical asymptote after reflection becomes horizontal asymptote. So we have this line of height pi by 2, this line of minus pi by 2, and our function approaches these lines. So that's the graph of arc tangent. Let's discuss some important facts about this arc tangent. Arc tangent of 0. Well, that's easy. Some number whose tangent is equal to 0. 0. Yes. So tangent is sine over cosine. Tangent of 0 is sine of 0 divided by cosine of 0. 0 over 1. Okay, arc tangent. Well, no, there aren't that many values for which it's easy to compute arc tangent. Arc tangent of 1, what is it? Pi over 4, yes. So it's some number whose tangent is equal to 1, and that's pi over 4. Let me explain this with a picture. It's about this triangle. Degrees, 90 degrees, and 45 degrees. So tangent of this angle is the quotient of this to that. When they are equal, which means tangent is equal to 1, well, the angle is 45 degrees, which is pi by 4. Okay. Similarly, arc tangent of minus 1 is, well, minus pi by 4. If you change the sign of the angle, the sign for the numerator will become negative, and the denominator will not change signs. The whole tangent will change sign. So our tangent of minus 1 is minus pi by 4. But let's discuss instead this thing. So these are the simplest values, and these are also the important ones. Let's discuss these ones. Arc tangent of x. What happens when x goes to infinity with arc tangent? Yes, it approaches pi by 2. That's exactly what we see from this graph. So here we see that pi by 2 tangent has a vertical asymptote. After reflection it becomes horizontal asymptote. And we have this limit. And similarly, limit at minus infinity of arc tangent of x is minus pi by 2. So we see that it has two different horizontal asymptotes. So that's the part about arc tangent which does not involve calculus, or almost doesn't involve calculus. But the derivative, well, I mean, it's obvious that we can actually find it using implicit differentiation, using this equation, but let's not spend time on this. The derivative of arc tangent is 1 over 1 plus x squared. And in a way, of the three formulas, this one is the most important. Because, well, once again, it's about next course. In next course, you'll discuss integration, which is kind of opposite operation to differentiation. So you'll go from the answer of differentiation back to the function. And well, the only way you can do this to that function, you'll be able to go back to our tangent. So you'll definitely see this formula several times. So maybe questions about these formulas. Anything about trigonometric functions. Okay, then let's do some simple examples and so example, find the derivative such a function. Okay, so the problems with these functions, well, you can imagine taking any problem on, I don't know, chain rule, related rates, optimization, whatever. They now can all involve such functions. They should become as basic as the other functions, log e to the power sine cosine. So basically now our repertoire of function includes 3 more. And so we basically must remember this and know how to use this formula. So let's do some simple example. Here's an exercise obviously on chain. It's composite function, first e to 4x, and then apply arctangent. So the derivative of arctangent is 1 over 1 plus its argument squared times the derivative of the argument. So it is 1 divided by 1 plus e to the power 8x times e to the 4x times 4. Let's do one more exercise of similar kind, but a little bit more surprising. Before there's any questions about this one. So let's talk about the next one. What is derivative of arc cosine of sine x? Well, derivative of arc cosine is 1 over square root of 1 minus its argument squared, so it's minus sine of x squared times the derivative of sine, which is cosine. Well, on an exam, you're encouraged to leave it as it is, because on an exam it's better not to make a mistake rather than simplifying it and make a mistake. Now let's actually simplify this. So here I have 1 minus square of sine. But 1 minus square of sine is exactly square of cosine. So this is minus 1 over cosine of x times cosine of x. So the answer happens to be minus 1. So it looks a little bit suspicious, doesn't it? I mean, such a complicated function has such a simple derivative. And also you know, well, one function which has such a derivative, it's minus x. We shouldn't really expect too many different functions to have the same derivative. Well, there is a reason why this function has such a simple derivative. In fact, r cosine of sine of x is pi by 2 minus x. So, using some trigonometry, we prove such an identity, and see that using our knowledge of calculus, we guess that there must be some kind of such identity, even without actually knowing the geometry. I mean, we didn't know it exactly, but we just knew that it should be something with minus x. Here it is. Okay, so I will not explain this, and see you next time. We'll do some review.